For the next few lectures, we're going to be talking about greedy algorithms, and specifically we'll be focusing on techniques for proving their correctness. Many algorithms have to make a sequence of decisions, but greedy algorithms are ones that, by design, make those decisions quickly and never look back. Classifying which algorithms count as greedy and which ones don't can be a hard task. But in general, we'll think of greedy algorithms as ones that make the best decision in the moment without considering how that decision interacts with others in the past or in the future. For our first example of designing greedy algorithms, let's solve the interval scheduling problem. In this problem, we're given a set of requests to use some resource at various time periods denoted by a start and end time for each request. For example, the resource might be a classroom on campus, and the requests are different classes and clubs and other groups that want to schedule that classroom at different times of the week. So given a set of requests, we can think of the compatibility of different requests, where a pair of requests is compatible as long as they don't overlap. So if event I finishes before event J starts, or starts after event J ends, then those two are compatible. On the other hand, if events overlap partially or completely, then they are incompatible. And our goal is to find the largest possible set of events where no two events in the set conflict. So the collection is considered compatible as long as all pairs of events within that collection are compatible, and we want to find the largest compatible collection. And so we want to design a greedy algorithm to solve this problem. Part of the reason that we're interested in greedy algorithms is that they're often easy to implement and efficient to run. And this comes back to the idea from the beginning of the class that we should always start with a stupid, simple algorithm design and see if it meets our needs. One stupid, simple algorithm for the interval scheduling problem would be to try all subsets of the requests. For each subset, we could check if it's compatible, and among the ones that are compatible, find the largest. But before we even write that algorithm down, we can recognize how inefficient it would be, because the number of subsets is 2 to the power of the number of elements, and so we would definitely have an exponential running time. So perhaps the next simplest idea would be to sort all of the requests and then process them in that order, where when we come to a new event, we add it to the set if it's compatible with what we have so far, and reject it otherwise. This algorithm follows a common paradigm for designing greedy algorithms, which is to simply loop through the options and, one at a time, make a decision about that option. And often it can be helpful to begin by sorting the options into an order that will make it so that our on-the-fly decisions are more effective. If we think about the running time of this algorithm, sorting the requests should take n log n time, and then we will process all of the requests, and so this loop will execute big O of n times. And then within the loop, we will check the compatibility of the current request with the set of requests we have accepted so far. And in the worst case, this might take linear time if we have to check the new request against all of the elements in G. But hopefully, when we fill in the details in a moment, we can find a way to make this check take log n time or less, so that the overall running time of the algorithm will be no worse than the n log n required to do the sort. In my pseudocode so far, I have left the criterion by which we are sorting unspecified, and there are several options we could consider for how to sort the set of requests. Possible criteria to consider include the order the requests were given, in which case we wouldn't need to sort them and could skip that step entirely. Or we could sort by the start time of the request, which would be trying to schedule the things that begin earliest on the timeline as early as we can. Or we could sort by finish time, meaning that the events that end earliest will go first in our order. Or we could sort by the length of a request, the time from the start to the finish, which would prioritize shorter events. Or we could, for each request, count the number of other requests that it conflicts with and prioritize the requests that have the fewest conflicts. In this case, our sorting might take longer than n log n time because we have the additional processing of first figuring out, for each of the requests, how many conflicts does it have. So let's think about each of these criteria on an example set of requests and see if there are any that we can rule out as definitely not giving us an optimal algorithm. Here we have a collection of events where the bars represent the duration from the start time to the finish time, and we received them in the order A, B, C, D, E, F, G, H, I. So if we processed these requests in the input order, we would start with request A, and it's compatible with our so far empty set of requests, so we would pick A. Then, continuing in order, we would consider event B, and it is compatible with everything that is in the set so far, so we will add it to the set. Then we come to event C, which conflicts with A, and D conflicts with A, and as we continue through all of the remaining requests, they each conflict with one of the things we've chosen so far, and so we end up with a set of events that just contains A and B. What if we use the criterion of sorting by start time? Well, then we will first consider the event with the earliest start time, which is A. Next we'll consider G, but that conflicts with A, which we already picked. C conflicts with A, so do D and H and E and I. So next in our sort by start time will be F, so we'll pick it, but then B conflicts with F. If we sort by finish time, then the first request in our sorted order is C, and it's compatible with everything in the empty set, so we pick it. The next finish time is G, but that conflicts with C, so we skip. Next to finish is D, which is compatible with everything in our set so far, so we add D. Then we consider H, which conflicts with D, then E, which is compatible. Then we consider A, which has lots of conflicts, I, which conflicts with E, and then B, which is compatible and gets added. Finally, we consider and reject F. And so, right now, we can already say that the input order and the start time criteria gave us suboptimal algorithms. Recall that our goal was to find the largest compatible set, and we now have an example where there is definitely a compatible set of size 4, and when we ran the algorithm with these criteria, we got a compatible set that was smaller than 4, and so this counterexample proves that if we fill in start time for our criterion, this is not a correct algorithm. Next, we can consider the total length of the request. That again puts C first in our sorted order, so it gets picked. Then we consider E, which is compatible with everything so far, so we pick it. Next shortest is D, which is compatible and gets picked. Next shortest is B, which is compatible with everything we've picked so far, so we will add it to the set. And at this point, when we continue with H, and then F, and then I, and then G, and then A, we always find that they conflict with something we've already chosen, and so we don't pick any of those requests. And again, we got a set of 4 requests that were all compatible. If we want to sort by our min conflicts criterion, it would help to begin by pre-computing how many others each of our requests conflicts with. So by our number of conflicts sort, we will begin with B or F and select it. Then we'll consider the other of those two and reject it. Then we'll come to the things with 2 conflicts, and whichever order we process them, we'll end up accepting both. So we'll say that we pick C first, and then we pick I. Then we come to the requests with 3 conflicts. Assuming we process them in input order, we would first consider D and select it. Then we would see that E conflicts with I, G conflicts with C, H conflicts with D, so we'd reject all of those. And finally, we'd come to A and reject it due to many conflicts. So for each of these 3 criteria, we got a compatible set of size 4. And in fact, we could confirm exhaustively that 4 is optimal on this example. So based on this example, we have several candidate criteria that all gave us the best possible collection of requests. But it turns out that only one of these is optimal in general. In the remainder of this video, we will prove that the greedy scheduler using the finish time criterion is an optimal algorithm, but I will leave it as an exercise for you to come up with examples where these other 2 criteria give suboptimal results. Our textbook covers several approaches for proving that a greedy algorithm is optimal. The first approach is known as a stays ahead argument, and we'll see an example of this for our interval scheduling algorithm today. The second proof technique is known as an exchange argument, and we'll see an in-depth example of this next time. But for the third approach, matching bounds, I won't be doing a separate video, so it's worth taking a moment now to say what that's about. We've seen a number of examples already in this class where we can prove some kind of bound on performance. So if you can analyze your greedy algorithm and argue that it must get at least some given performance, and you can also analyze the problem and show that the optimal solution to the problem must have at most some value, then if you can make those 2 bounds match, where the lower bound on your greedy algorithm agrees with the upper bound on the optimal solution, then you know that your greedy algorithm is giving you an optimal answer. Where this proof technique comes up a lot is when designing greedy approximation algorithms, because then we may not have a proof that our algorithm is optimal. We might instead have a proof that it is close to optimal, where we do that by having not perfectly matching bounds, but bounds that are relatively close. But this is a topic that we'll come back to only at the very end of the semester. So for today, we'll use the stays ahead proof technique, where we will be thinking about the sequence of decisions made by the greedy algorithm. And we will be comparing that sequence of decisions to a hypothetical optimal sequence of decisions, and show, in some sense, that the greedy algorithm is always staying ahead of any possible optimal result. And if we can argue that it stays ahead all the way to the end, we can use that as a basis for proving that our algorithm does as well as it possibly could. So to analyze the collection of requests that the greedy algorithm generates, we will compare that to a hypothetical set of requests that's an optimal solution to the interval scheduling problem. So we can enumerate the elements of the greedily chosen set 1 through k, and the elements of the optimal set 1 through L, and we will compare the elements of these sets and use that comparison to show that the number of elements in the greedy set has to be at least the number of elements in the hypothetically optimal set. So if our greedy number is at least the optimal number, that must mean greedy is equal to optimal, because you can't do better than optimal. And so that would prove that our greedy algorithm gives us the largest possible set of compatible requests. We'll start by arguing that if we compare the ith element of the greedy and hypothetical sets up through the last thing in the greedy set, element k, whenever we compare corresponding requests in these two sets, it must be the case that the greedy request has a finish time no later than the corresponding request in the hypothetically optimal set. And the core reason for this is straightforward. It's that we sorted based on finishing time when we were building the greedy set, and so we picked the earliest possible finishing times that we could have, but we'll establish this rigorously with a proof by induction. Our base case is about the first request selected in the greedy set and the hypothetical set. And we know that the first request the greedy algorithm considers is always the one with the earliest finishing time out of the entire input set, because that's how we sorted. And we know that the greedy algorithm always picks the first request it sees, because that request is compatible with all of the no requests it has so far. So it could be the case that the hypothetically optimal set chooses a first request that has the same finishing time as G1, but it can't finish any earlier. I'm now going to change the color of some indices to emphasize the induction on I. So if we know that the first request chosen by greedy has a weakly earlier finish time, we can now proceed inductively to argue that if the previous request had a finish time that was no later for greedy, then that must also be true of the next request. For our inductive step, we want to show the implication that if the finish time for the ith request is earlier for greedy, then the finish time for the I plus first request will be earlier for greedy. So we hypothesize that this is true and try to conclude that in that case, this must also be true. After greedy has found the ith element, and we are assuming that at the ith element the greedy finish time is no later than the hypothetically optimal finish time. It will then proceed to look at the next requests in its sorted order. And so the things that come after this request in the order will be the next things with the smallest finishing times, and it will pick the first of those that is compatible with everything in the greedy set so far. But to find a request that is compatible with everything in the set so far, it only needs to consider the start time of those requests. We know that this is the latest finish time of any request that has so far been selected. And so if we find a request that has a start time that is after this finish, we know that start time is compatible with all of the requests that we've selected up to now. And as a complete side note from our proof, this means that checking compatibility on each step of the greedy algorithm is constant time, because all we have to do is compare the start time of the new request against the finish time of the last request we accepted, which in turn means that the greedy loop takes linear time and the overall running time of the greedy algorithm is just the n log n required to sort. But returning to the proof, if we think about the next element in the hypothetically optimal set, that element must be compatible with everything that greedy has chosen so far. Why is that? Well, we know that the optimal set is all compatible, so the I plus first element of the optimal set must start later than the end time of element I in the optimal set, which in turn means that it starts later than the end time of optimal I in the greedy set, because our hypothesis said that the greedy finish time for I was no later. If we consider the I plus first request in set H, we know its start time comes before its finish time, because that's true of every request. And we know that its start time must come no earlier than the finish time of the previous request, because H is compatible. And by our inductive hypothesis, we know that the ith request in G ends no later than the ith request in H. And so that means that the I plus first request in H is compatible with everything up through I in the greedy set, which means that the greedy algorithm will choose that request if it gets there, but if instead it gets to some other request first, since the greedy algorithm is going in sorted order, we know that it will have a weakly earlier finish time. So at worst, the finish time for request I plus 1 in the greedy set is this one, but it might also be earlier. And since the greedy algorithm will choose that I plus first request from H, or one with an earlier finish time, we have reached our conclusion and shown inductively that for any I up through the end of the greedy set, the finish time for the ith greedy element will be no later than the finish time for the ith optimal element. So in terms of the finish time of the requests, greedy is ahead up through the kth element. So all that remains is to consider whether there are additional elements in H after element K. But if there were, by this same reasoning, those elements would be compatible with everything in the greedy set. And so the greedy algorithm would not have stopped, it would have kept going and considered those options, found them compatible, and would have selected them. So that means there cannot be any additional elements in H beyond the kth, And so we have that the size of the greedy set is at least as large as the size of the optimal set. Which means that the greedy algorithm is choosing the largest possible set of compatible requests, and therefore gives us a correct solution to the interval scheduling problem.